Hello students, I am Manoj Kundare, the Assistant Professor of Electronic Science. Welcome back to our e-learning platform. In previous video, we have completed the second unit of the subject Semiconductor Devices and Basic Electronic Systems. In this video, we are going to start the unit third of the subject named as MOSFET. The MOSFET is an acronym for Metal Oxide Semiconductor Field Effect Transistor. That means it is an electronic device which belongs from the FET family or the field effect transistor family. Okay, it is a device in which the variation in the voltage determines the conductivity of the device. That means the FET or the MOSFET is a device in which the input voltage determines the output current. Okay, or the output current depends on the value of the input voltage. The MOSFET is an unipolar device. This is the very important statement here, that MOSFET is an unipolar device. That means in MOSFET the current flows due to only holes or due to only the electrons, while the BJT is called as the bipolar device, because in BJT the current flows due to both holes and electrons. I hope you all get the basic difference between the unipolar device, that means MOSFET, and the bipolar device BJT. MOSFET is also known as IGFET, that is insulated gate field effect transistor. MOSFET is a three-terminal device which has the three terminals such as source, a drain, and a gate terminal, while BJT has the three terminals such as base, emitter, and collector. The MOSFETs are the voltage controlled devices. This is the another important statement here, that the MOSFETs are the voltage controlled devices in which the current flowing between the source and drain is proportional to the provided input voltage. That means, as seen previously, the input voltage decides the value of the output current, or the output current is totally depends on the value of the input voltage. Hence this device is called as the voltage control device, while the BJT is called as the current controlled device. Okay, now let's see the types of MOSFETs. Mainly there are two types of MOSFETs: depletion type MOSFET and enhancement type MOSFET. Further, these enhancement and depletion type MOSFETs are divided into two types: P channel and N channel. Okay, that means P channel enhancements MOSFET, N channel enhancements MOSFET, or P channel depletion MOSFET and N channel depletion MOSFET. Let's see the basic difference between depletion type MOSFET and enhancement type MOSFET. In depletion type MOSFET, a channel is already constructed physically and gate to source voltage is needed to switch the device off. That means in depletion type MOSFET, the channel is present physically, okay, or the channel is constructed physically. There is actual presence of channel. But in an enhancement type MOSFET, there is no any pre-constructed channel existence is noticed. That means if this is the MOSFET and these are, suppose this is the source terminal and this is the drain terminal, then between source and drain, if the channel is present, then it is called as depletion MOSFET, and if the channel is absent, that means if this channel is absent, then it is called as the E-type MOSFET or the enhancement type MOSFET, because here no physical construction of the channel is present. The voltage applied across the gate is needed to create a channel for this conductance. Okay. Now let's see the details about the symbols of the MOSFET. There are total mainly two types of MOSFET: enhancement MOSFET and depletion MOSFET. Let's see the symbols of N-channel MOSFET. The N-channel enhancement MOSFET symbol is shown here, in which the arrow is inverted towards the gate terminal. Okay, similarly, in depletion type MOSFET, the arrow direction is inverted towards the gate terminal. Okay, the basic difference between enhancement and depletion type MOSFET is that here is the continuous line is present. This continuous line shows there is a physical construction of the channel, while in enhancement MOSFET the continuous channel is not shown, the dotted line is shown. That means there is no physical channel is present between source and drain in enhancement type MOSFET. Similarly, we can see here the symbol of p channel MOSFET. The symbols are similar to each other except the arrow direction. In p channel MOSFET, the arrow is outwarded from the gate terminal. Okay, its direction is opposite to that of n channel MOSFET. I hope you all get the basic difference between the symbols of the MOSFETs. Now let's see the construction of the depletion type MOSFET. First of all, let's see the construction of N-channel D-MOSFET. A lightly doped P-type substrate is taken into which two heavily doped N-type regions are diffused, which acts as source and drain. That means a lightly doped P-type substrate is taken. This is a lightly doped P-type substrate on which two highly doped or heavily doped N-type regions are diffused, which acts as this N-type region is acts as drain and this N-type region is acts as source. Okay. Then between these two N-type regions there occurs a diffusion to form an N channel connecting to drain and source. That means first of all we take a P-type substrate which is lightly doped. On this substrate two heavily doped N-type materials are diffused. These two heavily doped materials forms the terminals drain and source, and this drain and source are connected with each other through a N-type material which is known as the channel. Okay, the channel connects source to drain and it is physically constructed. A thin layer of silicon dioxide, that means SiO2, is grown over the entire surface and holes are made to draw ohmic contacts for drain and source terminal. That means above it, this is the layer of silicon dioxide is placed over the entire surface, but the holes are made for, that means here the holes are made for the contact of the source and drain terminal. Okay, these holes are made for the source and drain terminal. A conducting layer of aluminum is laid over the entire channel upon this SiO2 layer from source to drain, which constitutes the gate. That means over which this is the layer of aluminum is placed, and this aluminum layer constitutes or makes the gate terminal. The SiO2 substrate is connected to the common or ground terminals. Okay, I hope you all get the basic construction of this N channel D MOSFET. Let's see once again the construction of N channel D MOSFET. Okay, here is a lightly doped P-type substrate is taken. On this lightly doped P-type substrate, two heavily doped N-type materials are diffused. These two heavily doped N-type materials are, the first one is drain and the second one is source. These two heavily doped N-type materials are connected with the physical channel. This is known as the channel. Okay, and this is present physically. On this structure, a thin layer of SiO2 material is placed above which the aluminum layer is placed to make the gate terminal. Okay, this is the basic construction of the the N channel D MOSFET. I hope you all understand it. Now let's see the construction of P channel D MOSFET. The construction of P channel D MOSFET is also similar. That means here the N-type lightly doped substrate is taken, on which two heavily doped P-type materials are diffused. These two heavily doped P-type materials forms the terminals drain and source. These drain and source terminals are connected with the physical channel which is diffused by a P-type material over which a thin layer of silicon dioxide is placed. The holes are made for the source and drain terminal, and over this silicon dioxide layer the aluminum layer is placed to constitute or to make the gate terminal. I hope you all understand the basic construction of the P channel D MOSFET. Let's see the working of N channel D MOSFET. If NMOS, that means N channel D MOSFET, has to be worked in the depletion mode, the gate terminal should be at the negative potential while the drain is at the positive potential. That means if we want to see the working of N channel D MOSFET, then it is mandatory that the gate has the negative potential and the drain has the positive potential. That means gate terminal is connected with the negative terminal of the battery and the drain terminal is connected with the positive terminal of the battery. When no voltage is applied between the gate and source, some current flows due to the voltage between drain and source. That means when there is no voltage is applied between gate and source, that means when this source is absent, then current can be flow through in this direction. That means the holes are travels from source to drain. Okay, then let some negative voltage is applied at VGG. Now the next case is some negative voltage is applied at VGG, then the minority carriers, that means holes, get attracted and settle near the SiO2 layer, but the majority charge carriers, that is electrons, get repelled. That means we know that this is the P-type substrate, and in P-type material we know that holes are the majority charge carriers and electrons are the minority charge carriers. Here the negative potential is provided. That means this gate terminal becomes negative. This negative terminal attracts positive holes. Hence in this channel the positive holes are gathered while this negative terminal repels the electrons from the channel. That means the electrons goes away from the channel. Hence the current from source to drain is reduced with increase in the value of negative voltage to source supply. With some amount of negative potential at VGG, a certain amount of drain current ID flows through source to drain. Okay, when this negative potential is further increased, the electrons get depleted and the current ID decreases. That means as seen previously, as the negative potential of the gate increases, the more electrons are repelled, that means depleted, and here the holes are gathered. Hence the current from source to drain is now decreasing. Hence the current of the drain ID decreases. Hence, the more negative the applied VGG, the lesser the value of the drain current will be. The channel nearer to the drain gets more depleted than the source, like in FET, and the current flow decreases due to this effect. Hence, it is called as the depletion mode MOSFET. Okay. Let's see the drain characteristics of the D MOSFET. The bottom curve shows that the condition when no gate voltage is applied, due to which the negative value of drain current flows from source to drain. That means this area shows when there is no voltage is applied across the gate to source. The curve at the upper portion shows the condition when the gate voltage VGS is made positive, and the lower curves indicates the condition for the negative gate voltage. That means this area shows the VGS for negative and this area shows VGS for positive. Okay. Now this is the characteristics of the n-channel depletion MOSFET, in which the figure A shows the transfer characteristics and figure B shows the output characteristics. There are mainly three regions of operation: cutoff region, saturation region, and ohmic or linear region. For cutoff region, VGS should be less than minus Vt. For saturation region, VGS should be greater than minus Vt and VDS greater than Vp. For ohmic region, VGS should be greater than minus Vt and VDS should be less than Vp. I hope you all understand the basic operation of n-channel DMOSFET. Similarly, we can see the operation of p-channel DMOSFET. In p-channel DMOSFET, the gate terminal must be connected with the positive supply. That means this terminal should be connected with the positive supply. Okay. When we apply, when there is no gate to source supply is applied, then what happens here? Then some holes are flow from source to drain. Hence, the current flows at its maximum value. But when we apply some positive potential at the gate terminal, then what happens? This positive potential of the gate, that means this gate is now positive. Now the n-type substrate has the holes are the majority and electrons as the minority charge carriers. This positive supply attracts these electrons in the channel and holes are repelled due to the positive repulsion. Hence, that means the holes are depleted and the electrons are gathered across the channel. Due to this, the current from source to drain is decreased. That means as we increase the positive gate voltage, the current ID is decreases. I hope you all understand the working of the P channel DMOSFET. Okay. Thank you.